Good day, ladies and gentlemen. We are back to our discussions on linear programming. And today, what I intend doing is that we're going to, I recall that the last lecture we talked about how to plot inequalities, applied it to linear programming problems involving maximization, minimization. And we solve problems and the applications you can see from the exercises that we undertook last week or during our last lecture. Now, this lecture, what I intend doing is that I'm going to provide you a situation where you are not, or where your constraints are mixed. They are mixed in the sense that some of them are, have greater than or equal to signs. The other one can be less than or equal to sign, and then you have an objective function which you need to minimize or which you need to maximize. Right after that, I will also quickly or maybe leave you to look at the simplex way of solving linear programming problems. That is, if there is time. If there is no time, I will advise you to read yourself, once you are able to use the graphical solutions, I think you are fine. But those who are interested and would like to delve more into this can go further and look at the simplest method of trying to solve linear programming questions. Now, so these are more or less what we intend doing, and specifically I'll touch on the mixed constraint, some introduction on slack variables and the simplex approach. Though, as I'm saying, it may not be very relevant, but just for those of you who are much interested in this topic to go and look at that. Now, what do we call mixed constraints? You recall that when you talk about maximization, the constraints were less than or equal to, and then when you talk about minimization, the constraints were greater than or equal to during our last lecture. But then, what happens if some of the constraints, some of them are, less than, or equal to, and others are greater than or equal to? And there are really questions of this, real practical questions of this nature. And how do you solve questions of this nature? So, when you have the constraints being, greater than, it means talking about minimization, and when you have being less than, it means you're talking about maximization. So we are going to have a situation where the constraints are a mixture of maximization and minimization. And as usual, we will consider the non-negative, section of the Cartesian coordinates. A simple example, right? We have a profit function of this nature, and we have a constraint of this nature. Some of them are greater than, right? These ones are greater than, some of them are less than. And as I said, as usual, our non-negativity constraints are also imposed on the function. So how do we solve, an equation of, or a linear programming problem of this nature? The methodology is the same. What we need to do first is that we try to change all our inequality constraints into equality constraints and plot them. And then we try to look for, the most important thing is trying to look for the region that satisfies all these inequality. So when we come here, I have done the plottings over here nicely, right? You have seen the curves, and you can see that this is the region that satisfies all the inequalities. Right? This is the region. So what you do is that once you've plotted the curves, you take values. You can take a value like this, put it in all the three equations and see whether it satisfies it. You take a value here, put it in all of them and see it satisfies it, until you have been able to convince yourself that actually this is the region that satisfies all the three inequalities. Now, having done that, I told you that if this, our function, is going to be maximized, our profit function is going to be maximized, that will be achieved at the vertex right, that if there is going to be an optimal point, it will be achieved at the vertex of the region. And we have these vertices, 1, 2, 3, 4. So what we need to do now is to find, the points at these vertices. It is not that difficult to find the point here. You can see straight away that it's what? 2, 0. Okay, the value of x is 2, y is 0. Here is 6, 0. So the problem may be finding the vertices that we have here, this one and that one. So you may have to solve this line and this line simultaneously, this line and this line simultaneously, to be able to obtain these vertices. Now, when we do that, we have these points. Our calculations give us these points. The point R is this, the point S is this. So the next thing is that when we slot them into our profit function, and here the question was maximization, right? So we are maximizing. So when we find the maximum, we can see that the maximum is what we have here and correspond to the 0.32.5. So that is quite easy, and straight away we go. Another question on minimization, right? Once we have another one, the first one was on maximization. Here we look at minimization, but then our constraint functions, our constraints are inequalities. So you see this one is greater than or equal to, greater than or equal, but this one is less than or equal to. The methodology is the same. This is the plot of what we have, and you can see these are the greater than equations, the two over here, right? So the region is this region here up here, and the less than the region is what we have down here, and this defines the region that we are talking about. As usual, the optimum or the minimum will be attained at the vertex, right? It's not difficult getting to know this point and that point, but here you have to use simultaneous equations to solve for the point here and the point here. And our calculations, give us this, all right, give us this. Calculations give us this. So when we solve this equation and that equation, we got this. So we are set. We try, and then we fix in the values over here. And looking at that, we see that the minimum attains over here. And the minimum value is what we can get over here. And it's attained at these points, 1.83, 873, and then 3.375. So what we've done here is that we've been able to introduce you to a situation where you have the constraints being minimum, and then maximum, but then you can have an objective function being a maximum or a minimum. And in both cases, you will use similar approach to solve the linear programming problem. I have some activities here, right? And please take your time and make sure you've done these activities. You may think it's easy, but as I usually say, the devil is always in the details. If you take your time and you practice or you do all these work examples in addition to those that you will find from the textbooks, it makes you better off than somebody who will not do it. So take your time and go through these activities. And if you have any problem, let's meet at the chat room. Now, I'll introduce you to a very simple way of trying to work out these using the simplest method. But as I said, it's not a required sort of area. But some of you who may be interested can take the opportunity and then go further. With the simplest method, what happens is that you use a step-by-step approach to be able to determine the slack variable that invariably turns the inequality constraint into an equality constraint that permits you to solve for the equation, solve for the solution of a difference equation. So if you look at our example, right? Assuming we have this inequality, right? There is something that we need to add to this, the left side of this inequality, to make it equal to the right side. I'll call that one S1, slack 1, right? So when I make the slack 1, if I put that value there, I don't know that value, but if I put it over there, I should have an equality sign. So that is a slack value, and that one, once I put the S1 here, I'll be able to express S1 in terms of the others. So what happened is that the logic here is that we are able to combine X and Y so that it is going to be less than the 34 that we have over here, but then to add something that will allow it to be equal to that 34 and use that in our equation. A specific example here may help us much. And let's look at this example here. I'll scroll you through. We have to maximize this, and we have a constraint of this nature. And these are your non-negativity sort of conditions that we always more or less add to this equation. So I've introduced my slacks over here, and assumes that the slacks too are positive values because of the less than sign. If they are not positive, they are not going to add up to what I have here. And once we have that, we have also our objective function, which we don't introduce any slacks to. Now, in our equation that we have, we can write the equation in this form. This is our usual equation, the 5, 3, the 2, and the 5. These are slack values that we've introduced, and this is, the constants of our equation, right? This is the constant of our equation. So the next point is that we take our time, and then from here we have a check. What it means that when we add all what is here, it should be equal to what we have over here, and then we put our negative objective functions over here. The difference we have is 11. So the slacks that we are going to add up, they should all be equal to 11 and should be equal to what we have over here. Further, there's a step-by-step approach where you know the key row, the key column, and then you use that to establish the function in an iterative method to be able to arrive at the solution. I'd like you to take your time and then go through these points, right, step by step, and you'll be able to satisfy yourself that the solution will boil down to what we have over here, right? You go and determine the slacks from one to the other, and it says an iterative method where you do one, you move the other one, and I've taken my time to explain this here, and I'd like you to, go through, and you'll be able to convince yourself that the maximum is where we are going to have over here in terms of the maximum X and Y and the maximum profit. Please, if you do have any problem, let's discuss at the chat room, but my emphasis will be on using the graphical solution since the simplest method is more for the mathematicians. And further, I've even elaborated on the steps, the simple steps that you go through to be able to solve this problem using the simplex method. I think we've come to the end of our discussions on applied mathematics for economists. Please, this is a very important topic, and you can see that in your daily life you'll be optimizing, trying to turn economic problems into mathematical problems, and using the mathematical tools that we've learned in differentiation, integration, differential equations to be able to solve them. Thank you very much, and all the best.